Thank you all for being back after lunch. I know this is sort of the heavy time of the day, so I'll start easy and then maybe accelerate a little bit towards the second part of my talk. Feel free to ask questions. So what I'd like to pick up is this question of how we integrate learning in safety critical systems. And the tools that I'm going to use are based on model predictive control. This has now come up sort of a few times in several talks throughout the workshop. There's probably time that we really talk about it. And what I'll do is I'll give you sort of a flavor of the different things that people have, and including ourselves, how we've thought about how you can combine sort of learning and model predictive control. That means I cannot go into the detail for all of these topics, but I'm then happy sort of to discuss more later on. Right, and I think model predictive control that's maybe also why it's come up so many times. It sort of sits at this space right in the middle between sort of control, learning, and optimization. The things that I'll be presenting are mostly work of sort of 3 PhD students. The first part is going to be mostly work from Lukas Heving and Marcel Menner. And the second part of the talk is built on work by Kim Wabasich, who's also here in the audience. And I think he's going to be very happy to chat more about the details later on. OK, but let me start and tell you a little bit more about the problem setup. So we're looking again at our control loop, and we want to automatically decide about control input. So I'm going back to talking about inputs and states. I think it's good that we're going back and forth, so we're all used to both notations. And the reason why we do that is that usually we want to increase the performance of our system. We want to make it more efficient, more productive. And there's many success stories now in the history of how automatic control has done that extremely well. And we think about all of these examples and also sort of industrial applications, there's usually a set of safety requirements that you have to additionally impose and would like to achieve. And here I want to be specific, so we can, of course, also think about safety in terms of sort of stability, maybe convergence to a set point. The type of safety that I will be talking about is in the form of a set of critical constraints that you would like to satisfy. And we usually write those as sort of a set of constraints, and I work in discrete time systems. So a set of constraints that I call X, and that's sort of the safety conditions on our state. And the reason why that's hard is because we work under sort of limited actuation. Any physical system doesn't have infinite actuation, and so that's why it's sometimes hard to keep our state constraints. Okay. The sort of tools that we have applied in the past is model-based techniques, because they allow us to be explicitly aware of those safety requirements and then not overly restrict our performance too much when we do that. And also here, there's sort of many examples, and it was great to see more to also have this example. This is our version of the little car racing autonomously around the track. And so this is nice. You can see that these things, they do work pretty well these days. So why do we need something else? The first reason is, well, even if you can sometimes accomplish a certain task, maybe you want to do that and even push the performance further. Or you want to reduce your design time because that is becoming more and more limiting of your method. Or you may be just thinking about a different application. And if we now think about robotics, large-scale energy systems, maybe medical devices, and there's a lot of new challenges coming up. There's very complex systems, dynamics, environments, a lot of disturbances and uncertainties coming in. And I think the fundamental difference is that these are usually not sort of the small stochastic uncertainties that we traditionally deal with when designing our automatic controllers, but there's rather sort of a systematic effect in our behavior that we're missing, right? And if you apply the standard tools, ignoring that, well then that can very often lead to critical failures. Okay, so the obvious idea is, well, now we have a lot more sensing, we can take measurements, so can we include this idea of now also leveraging sort of the online information that we're gathering in order to sort of incorporate more information about these effects that we have been missing so far, and then sort of get the performance up again. But we shouldn't forget that we still have these safety constraints there. And so pretty much everything that I'm going to talk about in this talk is focusing very much on sort of safety constraints. And I think this is maybe something that hasn't come up so much in the talk so far, and hopefully that helps and is maybe another perspective on the things that we can think about. Right. Okay, so we have safety constraints. And I think what also makes this problem potentially a little bit difficult to some of the other learning problems that we sometimes think about is that, well, we have this dynamical system that we have to control. So there's fundamentally, at every point in time, we have to apply a control input. And not acting or getting this action wrong in our setting is just not an option, because you are learning in closed loop for some system that's safety critical. And so the setting that we're thinking about is one where you really learn online and you cannot learn from failure. So we don't do this in simulation, because as also Andreas has said this morning, very often we don't have good simulators of this, and so we want to learn for the real system. Okay. So our goal is going to be that we'll try to sort of combine control theory with learning in order to move into that space and improve sort of performance in closed-loop dynamical systems. That's going to be our setting with safety constraints. Okay, so we can now start and sort of write down this problem that we'd ideally like to solve a little bit more formally. And so usually, we start by formulating our optimal control problem, and we write down our objective, which is minimizing sort of some cumulative cost over the entire task, and that can potentially go to infinity. If you want, you can also maximize the reward, but that's here you think about minimizing some cost function. And you want to optimize that cost for your dynamical system. That dynamical system can be subject to uncertainty, maybe parametric, maybe stochastic uncertainties. And because that is now an uncertain system, then usually what you want to do is you want to optimize over a policy sequence that can make use of information sort of up to that time point. Okay, now we are in the setting of safety critical systems, so what we're going to do is we're going to write down our constraints also in this problem. And so here's our set of state constraints subject to our input limitations. And I write these in the form of chance constraints because we have now this uncertain system. Okay, so here's a point that was already made by Andreas this morning, and I want to make again. So when I said sort of safety is constraints, I was slightly sloppy, because safety is actually more than constraints. Safety is constraints at all times over our task. And if you think about that, that's quite different. So think about sort of a vehicle that's flying, and it's flying with a significant velocity downwards towards the floor. Then you need to react early on if you have limited thrust in order to be able to recover the vehicle. So just looking instantaneously at your constraint is not going to help you, because when you're there, it's too late. So therefore, I believe that if we want to think about safety in that sense and really sort of constraint satisfaction at all times, then somewhere we probably need to make use of a model to analyze what's going to happen sort of looking forward. Okay. So there's this problem, as I've just sort of written down my wish list, is of course not a tractable problem. And so also in this workshop, there's been sort of, I think, maybe two main things that how people have phrased this and tried to solve it. There's obviously the classical way of what we call model predictive control, where you basically look at this problem and then you try to write down sort of approximations and proxies for the cost, the constraints, and the dynamics, so that you can solve this problem numerically as an optimization problem in closed loop. That is now extremely well established, that sort of allows you to get constraint satisfaction guarantees, and sort of many people use that as their main method. Of course, that requires quite some experience and knowledge on how you do these and how you properly write down these proxies so that this works. And I think, so my point of view, if you think about reinforcement learning, sort of the goal is to get rid of that and not having to do that by sort of evaluating your objective empirically and then sort of improving upon it. And you can mostly in a gradient-based way, sometimes in a model-free way. The sort of the cost on that is that very often we lose these nice guarantees on constraint satisfaction, but on the other hand, we don't need all these sort of expertise in how we design that problem properly, because we just look sort of empirically at what happens. Okay, so what I like to do is sort of we're trying to bridge this and sort of use ideas from both techniques sort of to leverage the benefits of these two directions that we've been seeing. And I'll do that in sort of two parts of my talk. In the first part, we'll start building on a model predictive controller, because that has all the nice properties that we want. And then we'll look at how we can integrate learning into that. And then in the second part of the talk, we'll turn that around and say, okay, we're very happy with our learning-based controller. That may be reinforcement learning. And then we'll see if we can augment that with sort of constraint satisfaction guarantees. And I'll use sort of model predictive control concepts for that. Okay, so this is the theme of the two parts of the talk. So in order to talk about how we integrate learning in MPC, let's have a look at this sort of approximation that we're making a little bit closer. So when we write down our MPC approximation, and I'll just present sort of the nominal MPC problem. You can do extensions of that, but just think of the nominal MPC problem, which means we're sort of ignoring our uncertainties. So we're looking at a nominal dynamics model. And then the main idea of MPC is that you shorten your prediction horizon, so you're only looking ahead over a shorter time. But then, in order to compensate for that, you're repeating to solve that problem for every new measurement or estimate of your state that you're getting. So in the nominal case, you're now optimizing sort of over an open loop sequence of control inputs when you solve that problem. And then you're only ever going to apply sort of the first move, and then you're resolving again. So that's the main concept of MPC. And now there's sort of special components that I've highlighted here on sort of a cost and a constraint on the last element of my planning sequence. And we usually do that in order to account for the fact that I'm missing something in my cost because I've truncated my horizon, and I'm missing an effect of my constraints because I've truncated my horizon. Now, the theory of this, while if you just write down such a problem, it doesn't directly give you all the theoretical properties. So for nominal MPC, and I would also say sort of robust MPC, so under bounded uncertainties, the theory is today quite well established. And sort of the type of things that we like to prove when we talk about MPC theory is that, for starters, you usually have to worry about recursive feasibility. What does that mean? So if I solve that problem at the beginning of time, my initial state, and it's feasible, then I want to guarantee that if I solve this again in a closed loop, it remains feasible, because otherwise I do not have an answer. I cannot apply anything to my control plant. Okay. And then for the nominal case, directly sort of from recursive feasibility, you get constraint satisfaction, because if that problem is feasible, then your constraints are satisfied. And you can also prove things like stability, but as I said, that's not going to be the focus of this talk. So we're going to focus on constraints. Okay, nice. So what we've now realized is that you can interpret a lot of the things that have happened when integrating learning in MPC as actually trying to improve your approximation of this MPC problem from data. So you're trying to improve these elements that you now have, your cost, your dynamics, your constraints, by looking at the data. And you do that not necessarily to get the best proxy, but to get the best closed loop performance that you want it to have. As you can think about sort of learning in MPC, like doing that. And sort of while we usually quite intuitively think about the model being the most critical and important and difficult thing in MPC, there's more. You can, of course, focus on the dynamics model, but you can also focus on all these other components of your problem. And I'll go through these two now, mostly focusing on the dynamics model, and I'll comment a little bit on the second part. Okay. So how do we do learning-based modeling? So the main idea is usually we do first principles. Now you want to do I'm going to call it data-driven modeling, where you basically want to get rid of as many of the sort of model assumptions that you want to make. What we like to work with is sort of a combined approach, often called a hybrid approach, where we combine our first principles model that we can write down, and I'm going to call that a nominal model. And then I'm going to look at my measurements and then basically apply regression to the model error to then get such a combined model where I have a nominal model part and a data-driven model part. Now, you can do that offline and then just hand it over to your MPC and run with it. Or, of course, the ideal thing that we'd like to do, because maybe your system is varying, you want to do that in closed loop, and now all your data is now generated in closed loop. And I think that really is the case when this model makes a lot of sense. For control, we need to start driving the system with something, right? And this is our nominal model. This is supposed, the idea is that this is enough to just operate conservatively. And then we generate data, and then with that, we're going to improve the model going forward. Okay, so now there's different types of models that you can use. You can, again, and I'm going to call that again a nominal model for that, even though I call this a nominal model. But think about this as just looking at sort of the input-output mapping without worrying about uncertainties of that learned model. And there's different things that you can do. So we've seen sort of fitting linear models. You can do neural networks for that. What you are neglecting is that there's still some residual uncertainty in this. And if you really want to think about constraint satisfaction, this is the sort of thing that we really like to take into account. So our model is still uncertain, right? And I'll show you an example for that later. So now what you can do is you can say I'm taking a robust model. A lot of techniques are built on sort of set membership estimation, where basically the idea is that you're now trying to find a bound on that function from your data. And then there's a class of stochastic models where sort of we're trying to avoid making that assumption on a bound, but on the other hand, we're assuming some distribution, and then we're trying to leverage that distribution for the stochastic model. And there's one particular technique that's really become quite popular in that domain, and it's the use of a Gaussian process. So there's a lot of related work on that from Andreas Krause, also from Angela, who's talking on Friday. And when we started to look at this, we were basically just trying to find out, well, can we practically do that? So can we solve it in real time? Now, this is a problem that has to run in real time. We have to solve this problem. Can we do this for sufficiently dynamical systems? And that's sort of the type of question that I'm going to ask in this first part. So why does the Gaussian process make sense? And I think in particular, sort of this structure, having our nominal model with some term that we don't know, is where Gaussian processes are quite appealing, because all the structure that we put into our nominal model. And the rest of the model is really something where we don't have a lot of structure, and that's everything sort of that we couldn't explain. And the Gaussian process gives us a lot of flexibility to capture that. The other nice thing is that I directly get a distribution now, a posterior distribution for this function. And so I get an analytic description of my uncertainty. And so this flavor of thinking about a stochastic process, I think, is why sort of dynamical systems people really like to work with Gaussian processes. It's expensive, though. Here as well, I think that helps, because it allows you to define your Gaussian process and only a subspace of your states. And in addition, it may not even necessarily have to be a function of all your inputs, not all states, not all inputs. And an example, and that's the example that I'll also use afterwards of how you do this in practice, is this race car example that we've also seen before. So it's extremely easy to come up with sort of a physical, basic model of how your inputs relate to the basic dynamics. You just write down sort of a dynamical bicycle model that explains what happens when I basically push my throttle and steer. And you can also write down sort of a basic tire model, usually some form of Pateka tire model. But then, and that I think was mentioned by Ben also yesterday, the race cars are sort of tricky in that sense, because if you push them to the dynamical limit, then they become quite nonlinear. And then this nonlinearity and how you exactly describe your model all of a sudden becomes quite important. And because that depends on the tires, every time you race and over the course of your race, that's going to be slightly different. Right? And so this is why you can really not just take data from runs that you've done 2 days ago, fit your model, and then sort of start the race with that. And that's the idea why we do want to learn that online. Okay, what about the dimensionality? So here, if you think about it, that's sort of the simplest model that you can write down has sort of 6 states. You have sort of your position, the angle, and the corresponding velocities. But the uncertainty is really not in the position and angle states, but it's in your velocity states. So we can just define our Gaussian process in that subspace. And as a matter of fact, we're not even going to give it the position as an input, because we don't want it to be dependent on where we're driving, because then we would have very, very little data. And so we're only going to give it sort of the other states. Okay. So now it's the main task that we now want to integrate that model into our model predictive controller in order to take into account now that uncertainty prediction when we're doing our MPC and be cautious with respect to our constraints. So you want to take that residual uncertainty into account. So when you write that problem down, again, we're back to this previous point where this is not a tractable problem. So we need to go through some approximations to actually solve this. The first one is you realize that if you predict your Gaussian process forward, it's not a Gaussian distribution anymore after your second time step. And so that's the first part where you need to start. So you need to approximate that. And the really standard way of what people do is you basically assume that your function evaluations are independent and that you indeed approximate it as a Gaussian distribution at every prediction step. And there's different ways to do that depending on how much computation you want to throw at this. You can just look at your mean, you can do Taylor approximations, you can do moment matching. In any of these cases, what you're going to get is sort of an MPC problem that's now defined in your mean and in your covariance dynamics. And then once we have that, we can now also approximate our constraints. And we're going to rewrite our constraints basically as a function as constraints on our mean. And then sort of the tightening of the constraints of how much we have to back off will depend on the uncertainty, on the covariance. That tightening can be expensive if you think about very general type of constraints. If you think about simple half-space constraints, then this is pretty efficient to do. Okay, now here's the key part. That's still a really hard problem to solve, even after we've done that. It's a deterministic problem, nice, but it's still sort of a nonlinear, non-convex problem, and you have all the data points from your GP in there. And so what we've now done is a pragmatic way of approximating that, and it's an idea that we use all the time when we improve computation in MPC. And this is leveraging the fact that I'm solving this again and again and again. I'm not only solving this once. And my solution is only going to change a little bit every time I solve this again. Okay. And so what we do is we basically turn our GP model into a local sparse GP using just very tailored inducing inputs to get the complexity down here. And we're also going to pre-compute our constraint tightening. And I think so this is what we did and what works really well. I think there's a lot of space now for analyzing why that actually makes sense, and also thinking more about the type of optimization problem that we have and how you would solve this. What we do get is for this race car problem, we can get this down to 20 milliseconds because it's basically a problem that has complexity of a nominal MPC problem. And so what you can do is you can leverage all these very efficient tools that we now have in MPC, some of which coming out of Moritz's group, and here we use Casati, but then we combine it with sort of Forces Pro. So these are extremely efficient sort of nonlinear optimization methods tailored to MPC. That's leveraging the structure of MPC. Okay, so now we've done this for the small race cars, and then we had a wonderful master student and was really excited about this, and he wanted to do it for a big race car, which they also use in these student racing competitions. And so this is the result that we got at the end, where we basically, okay. Let's see if that starts. Right, so at the beginning, this is a pretty safety critical system. So what we're going to do is we're going to start racing very carefully with a nominal model, conservatively tuned. So we're just going to collect data for 2 laps. Then once we have that data, then we say, okay, now we have a minimal amount of information. So we sort of now start learning. And after that, we're learning really in closed loop. We continuously collect the data and update our GP at every point in time. And you see that sort of as you now go through the laps, from 1 going down to 7 laps, your lap times go down. And this is really because sort of your model becomes better and better. Well, actually, if you look at the model error, it doesn't really go down, but you're going much faster. And so your nominal model, which is sort of you get increasing model error because you're going much faster. And then if I show you sort of this 8th lap, then what you're going to see is just visually, this is not running, let's start again. Visually, you're going a lot faster than what you've seen before. These green dots, they're the data points, and so we select them online. So, we illustrate them on the track, but as I said, position is not really an input to this. And then you see in gray your prediction, and that's sort of getting a little bit wider every once in a while, so you can sort of phrase safely. And the point that I'd like to make is that even after you've learned, you will have model uncertainty. So it's not like you can all of a sudden throw that away, because this is after we've now learned for 8 labs and we've done really well. There's a corner, and the car, sort of, you can see that in the video, drifts a little bit. And the nice thing is that we see that because our uncertainty goes up. And so we were able to basically take that into account when we planned, so it was okay for the car to slip a little bit. So the point that I'd like to make is that model uncertainty is really critical to take into account with this, even after you've learned for a certain amount of time. Okay, so let me get to this part where, okay, I think we've seen that there's a lot of potential and they work pretty well. The performance is nice. We've seen several examples. The theory is significantly sort of lagging behind this. And sort of the reason is obviously that we need to go through all of these approximation steps, but also due to the nonlinearities. And there's been some theory on what you can do here, and Andreas didn't talk about this, but they have some nice results where they can bound their estimation errors and then actually do some robust MPC on that. There's some results coming out of Rolf-Findeisen's group on analyzing sort of stability. But if you're really sort of in this in the unbounded case, the theory is really hard. And that sort of led us thinking about stochastic MPC again. And we went back to the literature and realized that sort of closed-loop dance constraint satisfaction is really hard in stochastic MPC. And so we went back to the very easy case of just analyzing sort of a linear system with additive noise. And we now have some nice results where we can prove closed-loop dance constraint satisfaction and recursive feasibility for certain formulations. And there's a lot of related work, and I think there's also there's a lot of space in this where we can do a lot more on the theoretical side to bring these things together. Okay. A few comments on the second part. So obviously, we can not only think about learning the dynamics model, but also the cost function or the constraints. And I very much agree with Anka that this is a part that we're often neglecting a little bit. So we think that this is easy because maybe we're given a set point and we're just tracking that. Very often, it's more of an economic cost, maybe, trying to do minimum time, or I'm trying sort of to do comfort, or something that's really hard to specify mathematically as a function of my states. And so here people have thought about different directions. There's certainly a use of Bayesian optimization, what we've seen a little bit from Andreas' talk, not in the context of MPC, but the idea is pretty similar. So basically you have parameters in your MPC problem, and then you use Bayesian optimization to optimize your closed loop performance. What you can do is we had these approximations of our infinite horizon, and you can think about learning those. And I think that's what Francesca's going to talk about. Okay, great, good. So we're going to hear more about this in the next talk. And then there's also things about learning your objective if you see an optimal demonstration. And this is what Anka's also mentioned yesterday. But we're thinking about it in the context of inverse optimal control, which is very much related to inverse reinforcement learning, but not with the difference that we're thinking about the constraints. And that sort of makes the tool set a little bit different that we can use. So maybe I'm going to skip the details of this. So basically what we've so people have thought about the objective. What we've now also thought about is the constraints, a little bit what Netschmiel has talked about yesterday, only that we take a slightly different approach and we sort of work with our optimality conditions more to identify the constraints. Okay. So, good. So why would we not always do that? Now we have our MPC controller, it has worked well, and we can learn the dynamic, we can maybe learn some of the other things. And I think it's really much more down to the objective. First of all, we need to have it explicitly. Plus, it should have some nice properties. It needs to be differentiable. Ideally, we'd like it to be convex in order for our optimization to work well. For the good performance, maybe we need a really long horizon, and that makes our computation really hard. And then sort of that's the part that I skipped entirely, and that's sort of the exploration-exploitation trade-off. And what we're currently doing is we just learn passively. So we just take all the data that's coming in, and then we learn our model, but we don't really think about how we actually take into account the information gain as we're now designing our controller. And this is sort of the question that's called dual MPC, or it's coming out of this classical question of dual control. And we're also working on some results that are hopefully coming out soon on that. Okay, and so that's the motivation, I think, why you could think about not doing MPC, and instead you do reinforcement learning, because you get rid of these assumptions on your objective. But what we'll see is if we can still use sort of MPC concepts to bring back our constraints. Okay, good. So that's the second part of the talk. So what do we want to do? So when we started, we said, okay, can we really just think about any learning method? We didn't want to be very specific on this. And can we introduce and augment this with constraints? And the way that you can think about this is sort of taking your learning input that's proposed to apply to the system, but then you filter that first in the sense that you ask, well, can I apply this safely? If yes, sure, go ahead. And if not, I'm going to modify it in a way that I can guarantee constraint satisfaction, again, at all times forward. Okay, so that's the idea. And sort of conceptually, we often think about that as a safe set, so some domain within my constraints in which I can happily stay without ever violating safety in the future. Okay, so what are the ingredients that we need to do? Let's parse that sentence. So we need to find out how we verify safety and just decide if we need to modify the input, and then what the modification is. And so we need to both available. And so in principle, can build this on two main ideas. On some safety controller that works, but maybe low performance, but at least gives you constraint satisfaction. And then based on that, you can compute an invariant set. And invariant is really sort of the cornerstone of what we use to talk about constraint satisfaction at all times, because that's invariance means it's a set in which we can remain under this controller. And once we have such an invariant set, and that is within our constraints, this is a safe set. So under the safety controller, we can then always remain here. Okay, so that's a principle, and if you think about a continuous time system, sorry, I'm going to do it for continuous time because it's easier to think about, then the strategy is very simple, so you can apply some learning input if you're inside the safe set, and then you're going to switch to your safety controller when you're on the boundary. Very simple idea. And so there's different techniques that have been proposed to do that. And I think historically the first one is what we today call control barrier functions. And here the idea is that you rather not explicitly compute your safety controller first, and the idea is built on rather control the of functions to do that. So at least as far as we understand it, that works well, but it's often difficult to design these functions, especially when you have multiple constraints. Then there's sort of a direction that's grown out of trying to compute now the largest safe set, and you can think about that as the maximum control invariant set that you can compute with reachability analysis, and that's sort of tools for reachability analysis that people have used here. I think there's a workshop right next week here at IPAM talking about sort of scalability of these things. I think it's fair to say that they have somewhat limited scalability in the dimension of the state space that you can handle with this. And then there's sort of direct approximations of these things, just doing convex optimization-based ideas. But these are usually conservative. Okay, so then we looked at this and said, well, what's the difficulty here? And if you look at all of these, the difficulty is that we explicitly want to compute our safe set. We want an explicit representation of that, and that makes it hard. So how can we avoid the explicit computation? And if you're coming from an MPC point of view, then, well, an approximation of your maximum control invariant set comes from your MPC controller. It gives you an approximation. So what the idea is going to be is that we approximate basically our safe set and the maximum control invariant set implicitly by using a model predictive controller. So what's the idea? So we're still assuming we have some safety controller, but this does now not have to work everywhere. Assume some small neighborhood in which this works. And then you can call a state a safe if you can plan a trajectory forward that satisfies all of your constraints and leads you to that neighborhood. And so we're going to say that's our safe terminal set that we would like to end up in, and as long as I can find such a trajectory, that's safe for all time forward. So if I want to verify if a proposed learning input is safe, then I'm going to ask, does it lead me to a state from which I can find such a trajectory? So I've reduced the question of safety to a planning problem. Oh, if you think about MPC, the question is always, why does it recursively work? It works once, is that going to work again? So if at the next point in time, you have another learning input that's proposed, and you're trying to go there, but you can't because you cannot plan a trajectory here, well, then you always have this trajectory from before that would be available and safe. OK, so you're safe. But ideally, we'd like to be minimally invasive. So we would like to modify the learning input as little as possible. And you can do that by basically not saying, I'm going to apply the learning input first, but I'm going to optimize also over that first step. I'm going to optimize over the entire trajectory, and then I'm just going to minimize the distance in some norm to my learning input. So if that learning input is safe, and I can afterwards find such a trajectory, then the optimal solution to that problem is the learning input. If not, it directly gives me sort of the minimal modification to it. So the nice thing about this, sorry, doesn't have, that I'm now writing my safety certificate by solving this finite time constrained optimal control problem. Gives me an implicit definition of my safe set, of my controller, deciding when I should be applying what. And because we now sort of built this on a sort of MPC concept, we can go back and leverage this entire range of efficient tools that we have available to compute these things. OK, so let's step back for a second and think about what happened here. So we've now basically separated constraints from performance. We're using some, say, reinforcement learning method for performance. The MPC doesn't know anything about performance. It only worries about constraints. And the idea is that this is often easier to do. So very often I can find a safe trajectory with a short horizon that satisfies all my constraints, but I don't get very good performance with that. Like for all the reasons that we discussed before. I would have to plan very long, and I don't have a very good idea of my cost function. And so I'm really only leveraging MPC now to do this planning within constraints. And everything else, I let the learning controller do.
Is the learning thing also doing MPC? Because they're running in parallel?
So we didn't do that. In principle, you could. So we, as you're going to see later, we're just tuning a simple PD controller, but you could also tune an MPC controller that doesn't know anything about safety, and then sort of use a simple short horizon planning in addition to that. Yes, you could do that.
You just need this thing to be sending you control inputs.
Yeah.
And you make them safe.
Yeah. Yeah.
How do you get your F?
Right, and that I'll talk about now. That's sort of my next slide. That's, of course, the cat. Thank you. You don't, of course, we don't know the correct model, right? And while I think doing just nominal MPC practically still makes sense, because we know that it often works, a lot of the research that we've now been doing is, thinking about how we can actually, what the model classes are for which we can write down some rigorous guarantees. And we've sort of went from thinking about sort of linear models with additive bounded noise to linear models with bounded parametric and unbounded additive noise, to now thinking about nonlinear systems with parametric unbounded disturbances. And we've also sort of started to think about distributed linear systems. I'm very happy to discuss it sort of offline. What I'd like to mention a little bit now is this nonlinear uncertain system part. I'm sorry. And what we're going to use here is a robust MPC concept. And we've also done that for some of the other things. What does robust MPC do? It basically starts saying I have some nominal model plus some error, and I'm going to bound that error and some error set, and you can generate that from data. And then you plan. And I've just learned in the discussion right before the talk that Dimitri was already thinking on doing something similar in his PhD thesis. So that's sort of, I've started later, but there's of course many techniques to do that. So you start planning basically with a nominal system. And then you apply, you can think of this as a tracking controller that you apply to your uncertain system, and it's going to try and keep you close to your nominal trajectory, so that you can really plan with your nominal trajectory, and then you simply apply sort of constraint tightening to also insert constraints on the uncertain system. So 100 ways of doing that. One that we found to be very appealing because it's super simple to implement is an approach that was proposed by Johannes Köhler. He's coming out of Frank Algover's group in 2018. And so the super simple idea is that you scale your constraints over the horizon. And now you relate that scaling basically conceptually to how fast you can and how well you can track this nominal trajectory. And so at the end of the day, you basically have 2 parameters to tune for this to get your robust MPC method. And that's sort of what I'll use. And I'm sure Kim's very happy to provide you with all the details. I'll leave it at that intuition. OK. So what's the difficulty if we could just do that? If we do robust MPC classically, we bound the error everywhere in our state space uniformly. And that can be extremely bad, very conservative, especially if you think about nonlinear systems and you think about learning, and we haven't seen a lot of data in certain domains, and then taking a uniform error bound makes this really bad. And so this is really, I think, where now we've started to think about how to make this a lot more practical. And in order to talk about this more, I'll work with this sort of parametric nonlinear system. We don't know the parameters, but we assume some prior parameter distribution. And so why does it give you, and what we'd like to do is now think about sort of state and input dependent uncertainties to improve on that uniform error bound. If you think about the linear parametric model and you now draw samples, you see that clearly for this linear function, you have different uncertainty in some parts of your state space than in others. OK. So what can you do? What we still want is we still want sort of safety, and we're going to call it the safety and probability because we like to satisfy all our constraints with a certain specified minimum probability. And then in order to be able to work with some form of a robust model, we'll again write down a nominal model with some nominal parameter estimate, and then write down an error bound in which our dynamics are going to lie with this minimal probability that we want. OK, as I said, so this is not the uniform error bound that we want to work with. We now do have sort of different uncertainties in our state space. And rather than bounding everything uniformly, we're going to turn that problem around. And we're going to say, well, let's first define an error bound that I'm willing to tolerate. And I'll then constrain my space such that this assumption is valid. So I'm writing this the other way around. And you can think about computing that explicitly. There's some work by Sebastian Trimpe on doing that. But we didn't want to do that because as you improve your belief about the model, you really would have to recompute this. And so what we're looking for is sort of an implicit description of that set. And I'm not going to go into a lot of detail on this. Basically, you can't predict, as we've seen before, you can't really predict with this uncertain model. So I really have to go to this other side. It's not going to work. OK, so what we do instead is we sort of use a bound on where our dynamics lead us. So some confidence map to describe our local uncertainty. And then once we have such a confidence map, we can impose that this has to lie within our maximum error that we're willing to tolerate. Sorry. So now in my planning problem that I've had before for getting safety, I write down everything now for my nominal system, and then I do my constraint tightening that we've had before. And now I have this nice implicit constraint that wherever I plan, I need to do that such that my modeling assumption is valid and I only have a maximum error. And under some, if you do Bayesian regression and you have normal distributions, then you can nicely write down such a constraint. And I think this is really sort of a critical novelty, which makes this practical. Is that you cannot take your worst case error bound, but we give you sort of your tuning knob, where you first say, I decide how much I'm going to be willing to tighten my constraint. So that's the error that I can tolerate. And then you plan such that that assumption is valid. And if you're initially feasible, then you have an all-time safety guarantee. Now, what happens if you're not initially feasible? Then two of the things can happen. Well, you either tighten your constraints more, or you realize that the probability of being safe that you've specified is inconsistent with how much you know about your model. Right? And you cannot be safe with that probability with how much you currently know about the model. So you need to work on either of the two. OK, so that was the idea. And in the remaining few minutes, I'd like to show you an example. And we'll start with a nice illustrative example. We've seen pendulums throughout. I'm happy it's a nice illustration. We're just going to work with sort of a one-link pendulum that we need to swing up from the downward position to the upward position. But we're going to make this a little bit harder by saying we have a constraint. So you cannot swing over, and I cannot swing back significantly. And this is, so our input constraints are such that you need to swing back. So you cannot just, you don't have enough torque to pull this up. OK, so.
You have actuator constraints too.
Yes. Yes. Sorry. Yes, you have input constraints. Sorry.
Actuator constraints.
Actuator constraints, state constraints. Yes. OK, and here's our model belief. So we start with just a few data points at the downward hanging position. And so here our model uncertainty goes up if we leave that space. And here you see this in 3 dimensions. And here you're going to see sort of the inputs that we apply. Which policy do we learn? We just do a bang-bang policy and do stochastic and gradient descent on it. And then we use a linear Bayesian regression model, as I said, for this. OK, so let's see what happens. So you start, and this is your safe trajectory that you're planning. So you're basically saying, I can safely go to a point as long as I can safely plan a trajectory back to my downwards hanging position. So then I'm good. And so as you now go through these episodes, you're going to see more and more information about your model. So you're getting more and more confident. And as you're getting more confident, you can accomplish this task. And actually, ultimately, and here you see the actuator limitations. And you can swing it up without ever violating your constraints. And that's actually a really hard problem to do with other control methods if you try that. Right? OK, so that was sort of a toy problem. It's always nice to do. And we said, OK, can we do something a little bit more advanced? So let's think about a quadrotor. And I know Ben said a quadrotor is easy, but it's only easy if you just control it to a set point. And what we're trying to do here is minimum time. Right? They're trying to go from one point to the next in minimum time. And you can do that with very simple controllers. And sort of Andreas also said that. PD controller is actually enough, but how do we tune it for minimum time? Right? And so what we're going to do is we're going to use a PD controller to control the quadrotor from one point in the space to the next. And we're going to run Bayesian optimization to figure out the best parameters of a PD controller to do that. And then we're going to apply our predictive safety filter to make that safe. OK, so clearly, when I just do tuning of these PD parameters, what happens is if I go to a set point very close to the floor, I'm going to hit it. Every time I'm going to try and learn that controller. I think in the next one again, so there, you hit the floor. So if you now do your safety filter, then, well, planning for safety is really easy. You just say, OK, up there, I have a safe space. And I know a simple controller that works. And as long as I can plan a trajectory that would always bring me back to that safe space, I'm good. And then I'm going to indicate our activity level of the safety filter, so how much we modify our input. Now we do the same thing again. So we start, and now we realize that we cannot go down as we did before. So we're going to modify that control input. And so now we can similarly as before, so we iteratively learn to do minimum time control, but we do that such that we never violate our constraints. Okay. And now here you see all the different episodes with a safety filter and without a safety filter. Without the safety filter, at the beginning, you continue to hit the floor. So all these little things are indicating that you hit the floor with one part of your quadrotor. And with the safety filter, you early on realize, that this is not a good idea to do. And so you're much faster actually converging towards this optimal trajectory that does your minimum time control at the end. Okay. So with that, I'd like to conclude. So what have we been talking about? So we started to think about sort of doing learning control for safety critical systems, and the main thing was how do we satisfy our safety constraints. And at the beginning, so we were built on MPC and said, okay, MPC is a good idea, but very often I don't have a very good idea of how to specify all these MPC elements, and we're going to do that from learning. And one approach that I've shown you is sort of use a Gaussian process model to do that, because we can take into account the uncertainty and then sort of do cautious high performance control. And now in the second part of the talk, we wanted to do safety for any learning-based controller, and we've used our MPC concept for that to get an implicit, very scalable safe set and controller. I think the key idea that we want to take away is that this planning in a confident subset is extremely critical to make these systems work practically, because otherwise they can be very conservative. And what you get is a very nice modular approach by the separation, right? So you're not affecting your performance controller, and you can tune that and do whatever you want it to do. And we're only going to check whenever we have to intervene, basically, with this MPC controller. And we're going to do that in a minimal invasive way. Okay. So let me just sort of put up this thank you slide again for the PhD students that have worked on these results. And I'd like to mention that we also have a few open positions if you're interested. And then I'd like to thank you very much for your attention.